Now we're going to do our last topic in our memory and caches section. We're going to talk about program optimizations that consider caches. Okay? So the optimizing code for the memory hierarchy has, essentially boils down to write code that has better locality, okay, that has better locality properties. And remember, there's two types of locality: spatial locality and temporal locality. Okay, and spatial locality, what we want to do is to make sure the algorithm accesses data contiguously as much as possible, even lays out data in memory in a way that increases the spatial locality properties. And the second one is temporal locality. Makes sure the code should make sure that if there's a data item that's going to be accessed multiple times, try to access them closer in time. So you can take advantage of temporal locality and increase the likelihood that the data is going to be in the cache. Okay? And ways of achieving that, there's multiple ways, but two basic ones. One is a proper choice of algorithm. Of course, the algorithm itself determines a lot of how the data is laid out and how the order of the operations in the data. And the second one is loop transformations, how to reorder loops when you're traversing data structures. So let me give you an example that's going to showcase how important this is. We talk about matrix multiplication. In matrix multiplication, what happens is the following. For example, suppose that I have a matrix C that I'm multiplying that receives a multiplication between matrix A and matrix B. So this element here of C, which is element I, comma J, is equals the first column of the ith row of A multiplied by the first row of column J in matrix B, plus this one times this one, plus this one times this one times this one, and so on. Okay? So that means that this loop here, I don't want to read the code in detail because it's going to be hard for you. So, but what you need to understand is that this code is reading this, and then reading this, then reading this, and reading this, then reading this, and so on. So it's going to read the entire row of A and this entire column of B, just to produce a single element in C. Okay, so this is a matrix that's n by n elements. Okay, so we're going to do n squared of these operations. Okay, so it's a lot. It could be, especially if the matrix is big, this could be a lot of operations. Okay, so now let's do a cache miss analysis of this matrix multiplication. Okay, we are going to assume that matrix elements are doubles. Okay, so they take 8 bytes. Okay, and if our cache block is 64 bytes, each cache block holds 8 doubles. Let's also say that our cache size C, capital C, is much smaller than n, okay, which is the dimension of which is one of the dimensions of our matrix. Remember the matrix n by n. So let's see what happens in the first iteration. Remember that in the first iteration we're going to read the entire row of this matrix and the entire columns of this matrix. Okay. So one thing to keep in mind too, that the way data is laid out in memory, what we're doing is we are storing an entire row in memory, then another row, then another row, then another row, and so on. So let's say if this is row 0, row 1, row 2, and row 3, the way it's laid out in memory here is we're going to have entire row 0, then entire row 1, entire row 2, entire row 3, and so on. Okay? So the number of misses that we're going to have is going to be what? It's going to be n divided by 8, because as we're reading this one line here, we know that since each line here, each cache block has 8 doubles, okay? So like 1, 2, 3, 4, 5, 6, 7, 8. We're going to access the first one, it's going to be a miss. Then the second one is going to hit, a hit, and then the next one here is going to be a miss. So that's why it's n divided by 8. Okay, that's taking advantage of that because of spatial locality. We're taking only n over 8. Okay, now we're going to add n here because for each column here, okay, so for each column we're going to, sorry, for this column here, for each row of this column, we're going to have a cache miss, right? We're going to miss on this one, and then this one, this one, this one, this one, this one, for like all of them, because just this is bigger than a block. Remember that if the cache is much smaller than n, definitely a block is much smaller than n. Okay? So, and then when we are done with this iteration, only this part and this part here is going to be in the cache. And why is it? It's just because we just read the first element and everything else we didn't read. Okay? Great. So we're going to have 9n over 8 misses for the first iterations. Now, if we extend this to all of the other iterations, what we're going to do is going to have 9n over 8 misses multiplied by n squared, which is the number of iterations. Remember that we're going to do this. This is n by n. And we're going to do this for each one of the elements here. So that means there's n square elements. So that means that our final cache miss, the number of cache misses, is 9 over 8 multiplied by n squared. So it's a lot of cache misses. Okay? So one way to solve this problem is to do what we call a blocked matrix multiplication. So instead of doing an entire row and an entire column, we're going to do this block by block, okay? Such that we're going to, when we read a part of A here, we're going to read all of these, and then for B here, instead of reading just the first one, we're going to read multiple rows, okay, but smaller, and a subset of the row, such that this stays in cache and this stays in cache. Okay? And then when we need to cycle over this multiple times, we're not going to have to pay the miss again. Isn't that cool? So now let's do a cache miss analysis of this one. Okay? So now how many blocks are we going to have? Well, we're going to have n over b blocks because b is the size of the block. Okay? So, and we know that 3 blocks fits in the cache. Okay, so that means that 3b squared is smaller than the cache size c. So now what we're going to have is we're going to have b squared over 8 misses for each block, right? Because I asked this repeatedly, and then so if we do when we add this up, we're going to have 2n over b times b squared over 8. Which ends up being nb over 4 misses. So now in the end, after we're in the cache, what we're going to have all of this because we access all of these blocks that happen to still fit in the cache. Isn't that cool? Great. So now this is in the first iteration. When we do this over all iterations, all of them are going to be the same as the first one. We're going to do this, but now since we are dividing, we're doing this in blocks. Now we're doing n over b squared. That would be the number because we're going to do this once for each block. But now we're going to do fewer times. We're going to do n over b times squared. Okay. So in the end, what we're going to do is our cache miss is going to be n squared divided by 4b. So there's a huge impact in our cache miss. So in summary, if we don't do blocking, we're going to have 9 over 8 n squared misses. But if we do blocking, it's going to be 1 over 4b multiplied by n squared misses. Okay? So if b equals 8, the difference is 36 times. If b is 16, the difference number of misses is 72x. It's just really, really, really big. Okay? So, and the reason for dramatic difference is that matrix multiplication inherently has temporal locality, but you have to reorder the operation in order to take advantage of that. Okay? So the input data is 3n squared, and the computation is 2n cubed. So every array element is accessed order n times. Okay? But the program really has to be written properly, otherwise the temporal locality is too far apart in time, and the cache can't capture it. Okay? So the important thing to keep in mind for cache-friendly code is that the programmer, you, can optimize code for cache performance, but it really depends on how the data structures are organized, how data are accessed, how the loop nest structure works, and think about blocking, because blocking is a general technique. You can always try to reorganize how the order you do things such that you try to keep only a block, only parts of it in memory. Okay? So, and one thing to keep in mind is that all systems like cache-friendly code, but to get absolutely optimum performance really depends on the platform, because it depends on knowing the actual cache organization, cache geometry, things like cache sizes, line sizes, sensitivities, and so on. Okay. So you can get most of the advantage with generic code. Okay, so when you're writing generic code, just keep in mind that keep working set size reasonably small, so it fits in the cache and you take advantage of temporal locality. Uses small strides, so you take advantage of spatial locality, right, because it tends to be close by. And focus on inner loop code, because those are the ones that are going to be accessed close by in time. Okay, let's end our memory and cache section with what we call the memory mountain. Okay, this is very cool. Again, we run some experiments in Intel Core i7. Okay, and what we're showing here in this axis is read throughput, megabytes per second. So that means up is good, is better. Okay, and our L1 cache is 32 kilobytes. So, and this is the working set size, which grows this way, and the stride size grows this way. Okay? First thing to note is, as you increase the stride size, you see there's a general drop in read throughput, because you're not taking as much advantage of temporal locality. Now the other thing is, if you increase the working set size, if it fits in the L1 cache, you have really good high throughput. But then as it doesn't fit in the L1 cache now, we're going to drop to the other plateau here, which is whatever fits in the L2. And then the next plateau is whatever fits in the L3. Whatever doesn't fit in the L3, you have to go to memory. Isn't that cool? So that means if you keep the working set size as much higher, small, there's much higher chance to stay within the L1, which is good, or with the L2, and so on. So things to keep in mind is take advantage of spatial locality, so you keep the stride low. Take advantage of the working set size. You can do blocking to keep to focus on the working set size for parts of your code. Okay, and if you keep it small, you're gonna get very high throughput, which has a huge impact in performance. This concludes our memory and cache section, and I'll see you soon.